All right, so get this stopwatch started. All right. So we started talking about ponding, explained this idea of rain, or you have to consider snow as well. This idea that if you don't have enough strength or stiffness in your members, you essentially get this P delta behavior where as you inundate the roof with snow or rain, you get deflections. And then those deflections allow for the deposit of more rain or more snow, and then you end up with this effect that you can't keep up from, right? You don't end up getting equilibrium and the structure fails. I also mentioned some things about the fact that, in Bozeman, in our area, because our minimum snow load is so high, that ponding generally doesn't control. But there are instances where it just makes sense to go back and check some of the ponding analysis methods that are provided in Appendix 2 of AISC, which are really quick and easy to do just to confirm your structure is adequate. As I mentioned, every bay could be susceptible or could not be susceptible. It depends on the sloping of the roof, the orientation of some of the members. And we went through kind of those 4 different conditions where it's required to check, or what's considered a susceptible bay. And so we went through our 2 methods. We have a simplified and an improved. Simplified is very short and easy. It's very conservative, where you get this flexibility coefficient, CP or CS, for each of your members. So you have your primary members and secondary members, primary being your girders, secondary being your joists or beams that are framing into it. And the response, or this flexibility, is based on the length and the moment of inertia. As you can imagine, that makes sense that that would contribute to the overall displacement is length over moment of inertia. And so we went through the simplified and improved. One of the big things with the improved is that we need to look at the actual stress that's going on based on ASD level loads and the load combinations associated with it. So if you were dealing with rain loads, you'd have to look at the rain specific combinations, snow load specific combinations. And so you end up utilizing these figures that have a graph on them, where you enter the graph with your stress index for either the primary or secondary direction. Then you go to your calculated flexibility coefficient for the opposite, so either the secondary or primary. And then you end up getting out of that the upper limit for CP or CS. There are a couple special cases we went through as well. So let's go through an example really quick, really straightforward. So we have an industrial building with 40 by 30 foot bays and a flat roof. Girders are W24 by 68 beams and, are W24 by 68. Beams are W18 by 40, spaced at 5 foot on center. The controlling roof loads consist of the dead plus snow load ASD case, with snow load being 40 pounds per square foot. They have in this building a Volcraft 1.5B 18 gauge deck that they're using, and we want to see if we have any ponding issues. So it is a flat roof. In that case, we're going to have susceptible bays. So we're going to just check a generic interior bay. So if we look at the simplified procedure here, we get our CP, right, and our CS are the 2 flexibility coefficients we're going to want to calculate. So that is 32 times LS times LP to the 4th, all over 10 to the 7th IP. Well, the length of our secondary members, well, if it's a 40 by 30 bay, we're going to use our short direction for our beams. So we're going to say LS is 30 feet, LP is 40 feet, and the moment of inertia of a W24 by 68 is 1830 inches to the 4th. That being my favorite wide flange beam section, as we've talked about before. So CP then ends up being 32 times 30 times 40 to the 4th, all over 10 to the 7th times 18, 30 inches to the 4th. Making sure you use the units that they specify up here out of ASCE, right? So our lengths are in feet, our spacing of members are in feet, and our moments of inertia are all in inches to the 4th. So that ends up with 0.134. If we look at CS, 32 times the spacing of our members times LS to the 4th, all over 10 to the 7th times IS. Spacing, I mentioned, was 5 feet. The span of our secondary members is 30 feet, and IS for a W18 by 40 is 612 inches to the 4th. So we get 32 times 5 times 30 to the 4th, all over 10 to the 7th, times 612. We end up with 0.021. Right, so one of the equations required that we have to meet in order to ensure that we have adequate stiffness and strength is CP plus 0.9 CS. Has to be less than or equal to 0.25. So we take 0.134, add to that CS, 0.9 times 0.021. 0.021 is a very low value for CS, so we have very stiff secondary framing. We get 0.153 is less than or equal to 0.25, right? So we're good there. The second aspect is the deck moment of inertia. So the deck moment of inertia has to be greater than 25 s to the 4th times 10 to the negative 6th. So that would be 25 times, wow, everyone's just calling me right now, times 5 to the 4th times 10 to the negative 6th. We end up with 0.016. So ID has to be, the moment of inertia has to be greater than 0.016. So if we look at Volcraft, right, and I showed you in the last lecture some of those manufacturer tables, 1.5B 18 gauge, if we look here, right, the smallest of those moments of inertia, there's a little bit difference between positive bending and negative bending. So I'm just going to grab the smallest one to be conservative. So we had 0.277 inches to the 4th is greater than 0.016, right? So we're okay. So overall, therefore, we're stable for ponding. Using the simplified method, right, which is the most conservative. If we look at the improved method, just to go through the steps here, right, UP is our stress index for the primary direction. It's going to be 0.8 Fy minus F naught over F naught, right? So if we look at Fy, A992, didn't mention if we were using any other steel, so that's 50 KSI. F naught, well, that's going to be the stress, right, the maximum stress in our member as specified earlier. So with F naught, we're going to assume an interior bay. Why do we assume that? Well, in the primary framing direction is the girders. So if we looked at a girder, or I guess a typical bay framing, right? It looks something like this. Well, if we were at an end bay, then these members right here would then not exist, right? Which would then reduce the stress in our frame. So the conservative approach would be, let's look at an interior bay. It's kind of similar to what we have here. And let's look at this primary member where it has joist framing in from either side. So it doubles the tributary width, which essentially is going to double the stress. So we're going to go back down here. We're going to look at F naught. Assume interior bay. Another thing we have to come up with is the dead load. 20 PSF I'm going to assume, right? If I ask you a question in the homework or in the final exam related to ponding, I'd have to give you some information relative to dead load, right? I could either give you the dead load in pounds per square foot, or I could give you an assembly and then you could devise what that assembly weight is, right? Based on ASCE 7. So we have 20 pounds per square foot for a common dead load for a steel framing system. So we have dead plus snow is 20 plus 40 is 60 pounds per square foot. Our tributary width, well, our joists are framing in the 30-foot direction, so we get 30 over 2 times 2, or 30 feet. Our uniform load is going to be 30 feet times 60 PSF. That gives us 1,800 pounds per foot. Moment, right? Well, if we assume simply supported members, the moment within our girder is going to be WL squared over 8. Technically, we have 3 point loads, or I guess we have more than 3 point loads, but technically if we have a 40-foot span and it's at 5 feet on center, we really have 7 point loads in the interior of our girder, right? Which 7 point loads, you can actually look in the steel manual. They have a equivalent uniform load chart that allows you to take a point load and come up with the equivalent. When you get up to that, 6, 7, 8 point loads evenly distributed along the length, you're getting really close to a uniform. And we're assuming that it's uniform for this analysis method anyway. So I think at this point, I feel pretty confident about the uniform method. So we're going to say this is the assumed approximate uniform. So WL squared over 8, W we just figured out was 1,800 pounds per foot times 40 feet squared all over 8. I'm going to divide this by 1,000 so we get kip feet. We get 360 kip feet. So if we look at stress, ASD is going to be M over S. We get 360 kip feet times 12 to get it to kip inches, because we're going to divide it by S, which we get out of our dimensional table is 154 inches to the third. We get 28.1 KSI, right? So not that high, about 50%. That's going to be F naught, right? So now we can develop our stress index, 0.8 times Fy. So we're limited at 80% of 50 or 40 KSI minus 28.1 all over 28.1. All of a sudden we get 0.423. So we have 0.423. On top of that, as I mentioned, we need our C sub P value, right, that we had before. So our C sub P was not C sub P, we need C sub S, which was 0.021, right, 0.021. We're going to say C sub S equals 0.021. So we're going to start with our UP, which is 0.4, something like there, right? We're going to follow that line across until we hit I don't know, maybe that works. Somewhere in here, right? 0.21. We follow that line down, so line over, line down. Our upper limit, right? So our C sub P has to be less than or equal to, I'm going to approximate that as 0.26. C sub P was 0.134, so we're okay, right? And we should be okay. If we're okay for the simplified method, then we should be okay for the improved method, because we're just sharpening the pencil a little bit, and this is a little less conservative. So now we go to our U sub S. Same process here, right? 0.8 Fy minus F naught over F naught. Fy is still 50 KSI for W18 by 40s. We do dead plus snow, so we get 20 pounds per square foot plus 40 pounds per square foot times tributary width for one beam is 5 feet. We get 300 pounds per foot. So if we look at our moment, again, WL squared over 8. This one is truly a uniformly loaded beam because we have our deck sitting on top of our beams. 300 times 30 squared over 8 divided by 1,000 to get us to kip feet. We get 33.8 kip feet. Stress, right? M over S, same thing. We get 33.8 times 12 to get us to kip inches, because we're going to divide by inches. It's going to land us in, 68.4 is S or W18 by 40. We end up with 5.93 KSI. That's super low. So I'm assuming I'm going to get a very high value for use of S, right? Because we'll find that that high value is essentially providing us with a very high upper limit. So we have use of S is 0.8 times 50 minus 5.93 all over 5.93. We get 5.74. That seems crazy, right? We're way off the chart on this one. That's okay. We can extrapolate. I feel comfortable doing that. So if we look at the limit's going to be way up here, we're going to then travel across until we hit our C sub P value, right? Which is, if we look back up here, C sub P was 0.134, right? C sub P equals 0.134. So we're going to start up here. We're going to roll across until we get 0.134, which is going to be way over here. So I'm going to say that the CS limit has to be approximately 0.7. So CS is equal to 0.021, or way okay in this case, right? So therefore, this bay is stable for ponding. Right? And that's basically it for the improved method to calculate the susceptibility for our bay for ponding. So with that, I'm going to try and pull together a homework here probably next week, and we'll do something relative to ponding. Maybe I'll pile it in with something with vibrations too. But anyway, as we got, I should be in class on Monday. Stay tuned in D2L for any announcements, but so far so good. And we will continue moving forward.